Welcome back. We're putting the final finishing touches on this calculation of the predictive density for Bayesian linear regression. And so I realized that I should have simplified this a little bit first. Here we can make this alpha plus a alpha squared minus a alpha squared, cancels of course, plus a alpha. And now if we plug this in, we get lambda is a times 1 minus, I think it was, what was it, a times that thing, which is what we just computed. So that becomes a alpha over 1 plus a alpha. And then we simplify a little bit again, 1 minus a alpha, 1 plus a alpha minus a alpha, 1 plus a alpha, cancels again. There might be a simpler way to do this. And then finally we get a over 1 plus a alpha. This is just all little computations. But just to be complete, let's do it. And we get 1 over lambda. If we flip this over, we get 1 over a plus alpha, and alpha is x transpose lambda inverse x. So let's check and see if that's, yep, and that's what we wanted to show. That was the formula that I had claimed before, and we got it. So that's good, and now we need to check that u equals mu transpose x. So we would like to show that mu transpose x equals u, put a question mark. U, we know, is this: 1 over lambda ax transpose L inverse lambda mu. Gosh, can I remember that? 1 over lambda I forgot it already. Ax transpose L inverse lambda mu. X transpose L inverse lambda mu. L inverse lambda mu. Okay. Now what? So to show this, let's see. Actually, let's say, let's rewrite this. Let's transpose this. We can transpose this. Mu transpose. Is that what we want? No, actually, let's transpose the other side. This equals, what do I want here? Sorry. I do want to transpose this side. 1 over lambda mu transpose a times mu transpose. Actually, let's do it this way. Sorry, I keep changing my mind. Mu transpose, to make it look, I'm trying to make it look like this side. Mu transpose 1 over lambda a L inverse, no, lambda transpose equals lambda L inverse transpose equals L inverse x. Okay, that's what we want. Right. And so in order to show this, we need to show that x, it's equivalent to show that x equals this: 1 over lambda a lambda L inverse x. Okay. And we may as well, let's move the lambda, let's move the matrices over. This becomes lambda inverse Lx. We want to show this: 1 over a x, because these are just constants. This is, let's see, lambda, or L rather. What is L? L was what was inside of here. Axx transpose plus lambda. Lambda inverse Axx transpose plus lambda. X, multiply the lambda through, we get a lambda xx transpose plus the identity. Is that right? times x. And let me see. Something's not right here. Wait, what happened? We got here. Oh, of course. Wait, is that right? Yeah. Sorry. So this should have been. We wanted to multiply lambda first, so we needed lambda inverse. Now you can see how I messed this up so many times, doing it all over again. L times lambda inverse x. So this becomes lambda inverse on the right. And we get, a x transpose lambda inverse x plus x. And this was our alpha thingy here. I think that was alpha, wasn't it? Yep, that's alpha. So this is a alpha plus 1 times x. Okay. So in order for this to be true, we wanted to show this, and in order for that to be true, we need a over lambda equal to this, or in other words, we need 1 over lambda equal to this over a, and that is, that's exactly what lambda is, because this is alpha, right? 1 over a plus alpha. Okay, we got it finally. So that shows that this was true, and that shows that that was true, and that shows that that was true. And that's what we wanted to prove, that the the mean of that distribution over y equaled mu transpose x. And that was what we wanted to prove. So we got these two results. And that was what we wanted to prove. U equals mu transpose x, and 1 over lambda equals 1 over a plus x transpose lambda inverse x. So this is so cool. I mean, just to emphasize, this is so cool that we can actually get this expression in closed form. For such a general, I mean, this is a very, very general sort of problem. We're doing linear regression in high dimensions, and we're doing a fully Bayesian thing. We're integrating out this vector in high dimensions, and we can do it all in closed form. It's pretty cool. And the fact that it's so simple, this is cool. So let's see. Oh, right, there was one loose end we needed to tie up. Well, let's go back. Right, this here. We assumed that L inverse exists. We made that assumption, and let's check. Let's see. I think we can use this stuff down here. Where'd it go? L inverse. Right. I think we can use this to show that L inverse does in fact exist. So this is lambda inverse. We know lambda inverse exists. Make some space. Lambda inverse minus lambda inverse a x transpose lambda inverse. We're assuming lambda inverse exists. Actually, we proved that. If it were using it's the posterior mean that we computed before. 1 over a alpha. Alpha is this. And lambda inverse, in an earlier video, when we computed the posterior mean, remember that lambda inverse was the covariance matrix for the posterior distribution on W. And when we showed that lambda inverse exists in the sense that lambda is invertible, we actually showed that it was positive definite. We showed that, well, we know that lambda, because it's a linear algebra fact that since the covariance matrix is positive semi-definite, then, in fact, so the covariance matrix was positive. Let me see here. Hold a second. Right, the precision matrix is always positive semi-definite, and we showed that in fact it was positive definite because it was invertible. And a positive definite matrix, a quadratic form like this, where the matrix in the middle is positive definite, is always strictly greater than 0. It's always positive. That's in some sense why we call it positive definite. This is greater than 0 for any x. So this alpha is non-zero. It's, well, it wouldn't really matter that it's non-zero, but at least it's non-negative. It's positive. Actually, I guess we wouldn't have even need, we just need this to be, the covariance matrix to be positive semi-definite, and this would work. Even if this were just positive semi-definite, this would be greater or equal to 0. And then the denominator here would be non-zero because A is positive. Remember, A was the precision of above in our model. And so this is non-zero. Lambda is invertible. And so this expression is a well-formed expression. It makes sense. And by that Sherman-Morrison theorem, we know that it equals L inverse. And so that shows directly by exhibiting the actual inverse itself, that shows that L inverse exists. And that was the assumption that we made. So by observing that alpha here, that doesn't make this denominator 0, then we get that this expression exists and it must equal L inverse by the Sherman-Morrison theorem, by the Sherman-Morrison identity. It's also sometimes called the Woodbury identity. And that shows that L inverse exists. So we're all set. We're all good. And that, finally, if you stuck through with this to the end, then I applaud you. This was a lot of work to get this, but we got it finally. And so now we've got our hands on this beautiful predictive distribution, and I hope you found that was all worthwhile, and I hope you now have a better intuition and understanding for why the Gaussian is has the nice properties as it does. And just to sort of remind you why it all worked because these exponents were always these quadratics in the thing that we were interested in. Like, first it was a quadratic in W, and we integrated out W by showing that it was a normal, and then we got this expression for Y, and we showed that was normal because that was quadratic in Y in the exponent. And that was really the key step to all of this, is that the exponents always ended up being quadratics. So if there's anything that you remember from that, it's that thinking about the normal as e to the quadratic, and then completing the square in order to do this inference. That's sort of the fundamental thing going on in this calculation. So I hope that was instructive to you, going through the whole process, and I hope that you learned something from it.